Hey everyone. Today we're going to talk about the Earth's magnetic field. And as you've probably heard in other Earth science classes and things of that nature, the Earth's magnetic field has been known to change direction roughly every 10 or 20,000 years, according to the geological record. We're going to talk about a crazy theory as to why that would happen. Now, before I get into this, let me make sure it's crystal clear. This is not the official explanation of why this actually happens, but it fits nicely in with what we've been discussing lately in class. And if it were true, it would explain the Earth's B field direction change. With that disclaimer, let's move on. So here's a depiction of our planet Earth, and we know that there are two geographic poles to this Earth. There's the North Pole, which I'm going to put up here, and the South Pole there, and that dashed line, of course, represents the axis that the Earth spins about. Up here at the North Pole, we have a very famous resident, Santa Claus. We know lives at the North Pole, so here he is. And who lives down at the South Pole? Why, penguins live near the South Pole, of course. So we'll put a little penguin down there. But as we've already learned about in our physics class, there's something kind of weird about the north and south poles of the Earth when we talk about magnetism. What's so weird about that? You can hit your pause button and contemplate what's so weird about the north and south pole situation. Welcome back from your time on pause. And if you said what's weird about the North and South Pole situation of the Earth is that, in fact, the magnetic North Pole of the bar magnet that we could consider the Earth to be is actually down in Antarctica, and the magnetic South Pole is up in the Arctic Ocean, where Santa Claus lives. And if we were to draw the magnetic field lines of the Earth, field lines going north to south, outside here on the surface of the planet, they'd be going from where penguins live to where Santa Claus lives. Now, there's a long and convoluted story about that I won't fill this video with, but that's kind of where we're starting. So this is the Earth's magnetic field and how it's situated to begin with. But this video tries to talk about why it has changed direction historically. The arrows you see on the picture, in the past, they would have been drawn in exactly the opposite direction. If we were to look at this 10 or 20,000 years ago, in the past, the Earth's magnetic field has changed direction, as geologists know from looking at magnetized metal in the Earth's crust from tens of thousands of years ago. They've noticed that it's changed direction and changed back. So to understand why it changes direction, maybe we should come up with a theory as to why it has a magnetic field in the first place. And I will caution you, this theory is not the official theory of why there is a magnetic field on the Earth, but I think it's worth our discussion, so I'm going to introduce it. Let's think about why. To help us think about why the Earth has a magnetic field in the first place, we should ask ourselves, is it likely that the Earth is neutrally charged? Of all the countless trillions of trillions of trillions of trillions of trillions of particles on the Earth, do we think that there are exactly as many electrons as protons? I would say probably not. In fact, the Earth almost certainly has some charge to it. The sun is spewing out charged particles from its surface, launching them into space. Some of them collect on the Earth, and chances are the Earth is charged. So if we start with that presumption that the Earth is charged, we can then ask ourselves, what charge would the Earth have to have in order to be spinning and creating the field that we see in this diagram? Let's think about our spinning Earth. New York is right around here. Here's New York. And we know that the Earth spins such that the sun rises in the east for us. Well, if this is the east, then the Earth must be spinning so that if New York is right on the horizon in this picture, then New York is actually moving into the board. New York's velocity is into the board. And of course, here on the other side of the world, let's say this is Melbourne, Australia, over there, Melbourne is coming out of the board. So if the surface of the Earth, with all this charge we presume it to have, is going into the board over here in New York, coming out of the board over here in Australia, maybe we can ask ourselves, what charge must it have if it is creating the field that we see? And to answer that question, we really want to apply our second right-hand rule. So take a moment, think about applying the second right-hand rule, and figure out what charge the Earth must have. Hope you gave that a moment's thought. Now, the Earth is going into the board. So the charge that's on the Earth is also going into the board. We have moving charge going this way. Using my second right-hand rule, I've got my thumb pointed down into the board. And if we look at my fingers, oh, it looks like they're going exactly in the wrong direction. Now let's try it on the other side of the Earth. Here in Australia, my thumb is coming out of the board. And look at which way the field is pointing and which way my fingers are pointing. They're exactly opposite. So it looks like maybe the second right-hand rule is giving us a problem, but if you pause and think about it for a minute, actually it tells us everything we need to know. So while you were paused, did you think about what we need to know? It seems like the second right-hand rule has effectively told us the charge of the Earth, and that charge must be negative. A positive charge, moving the way it is, would give us the exact opposite field as the field that we get. So based on this theory, and again, once again, I must disclaim this is not the official explanation as to why the Earth has a magnetic field. It's a little more complicated than this. But if we imagine it as a solid unitary sphere with charge on it, the spin that it has would only create the magnetic field that it has if that charge were negative. But what we haven't addressed yet is why the field would change direction. Does the Earth's spin change direction? Probably not, right? There's no reason for the Earth's omega to turn around and start being in the other direction. We would need like a large comet or something like that to crash into us to make such a monumental change. However, the Earth's charge could change in sign. I'm imagining a positively charged particle, perhaps launched off of the sun, traveling towards the Earth. If the Earth were negative, that positively charged particle, of course, would be attracted to the Earth. However, as that positively charged particle approaches the Earth and enters into this magnetic field, it is moving towards the Earth. It's in a field pointed that way. It's going to feel a force into the board. So our positively charged particle flying towards the Earth gets pushed into the board, and chances are it gets swept behind and misses the Earth entirely. But some particles may have enough momentum that they do not deviate from that path and they hit the Earth, which of course makes the Earth a little bit less negative. And then that happens again and again and again until the Earth is neutral. Now the Earth is neither attracting nor repelling positively charged particles, but remember, before it was neutral, it was negative, it was attracting positively charged particles, and it has no reason for those, there is no reason for those positively charged particles not just to continue on their way, and then the Earth becomes positive. A positive Earth spinning exactly the same way would create a magnetic field in exactly the opposite direction. I can't disclaim this enough, so I'm going to do it one more time. That's not really why this happens, but if it were, it would explain the alteration of the Earth's magnetic field over time. Little exercise in right hand rules for us. I hope you enjoyed this video, and thank you for watching. Take care.